Okay, so these questions examine your understanding about the concepts of transformer. And example, right, for question 2 and also for question 3. For example, for question 3, for loaded practical transformer, explain why the primary applied voltage is greater than the primary induced voltage. Actually, right? So I explained during the tutorials. By drawing a equivalent circuit, showing you what does mean by the applied voltage VI, what is the internal primary induced voltage, and similarly, what does mean by the secondary terminal voltage, what does mean by the secondary internal induced voltage, and so on. So here, just checking whether you have understood that. So such a question serves as a examination about your knowledge about transformers. Some of it will appear in the homeworks assignment 1, and some of it will appear in the final examinations. So I can strongly recommend you that go through all these questions, check your understanding. If you do have some problems on understanding of such questions, you can write to me before the final examinations. So this is some of the questions. We have many such questions, serves as the self checking points. We also have several problems that on the ideal transformers, as we show here, problems 1, 2, 3. And the final direct answers are given here. So you can, for yourself, check it. If you try that, you can find out the answers. Sometimes we have some of the approximations. So some of the answers is not exactly as what you calculated later on. And also, sometimes maybe there is some type of errors. So if your procedures and the understanding is correct, generally your calculations, please believe it. So we have ideal transformers, we have practical transformers. That's the final answers. Figures be given here. And so we also have exercise on the single-phase transformers, on the three-phase transformers given here, with the answers be attached. So you can do it and check by yourselves. If you find the not correct, try it again and again. And finally, so if you can correctly solve it, that means that you have good understanding of the transformer. Okay, so this is the second part. That's the questions and the problems, which serves as the self exercise. And that's the part that we have some past exact papers questions. Actually, this is many years before. That actually some of the typical questions that show here. Of course, all these questions will not be again appear in the final examination because it is actually appeared very long ago in the final examination. But the principles showing there and the basic the solution steps, I think no matter how long it goes, it keeps similar because the scientific knowledge no more change. We just have the updates. Okay, we have several questions that showing you how to answer such questions in relative reasonable steps in the final examinations. Okay. Okay. So you look we have many examples given here, covered almost all all types of the possible exam questions for the three-phase systems. So every year we have questions on the three-phase transformers and their principles, okay, is similar. Okay. So there are many right examples on the three-phase transformer and single-phase transformer. Both the examples, both the exercise, and both the past paper exam. Okay, so you can refer to it by yourselves if you skip from these lectures. Okay, that's what I want to convey to you about the exercise. Similar combinations, similar set of exercise also be prepared for the induction motors and for the sequence generators later. So at that moment, I will not go through one by one of it. Just telling you would have been included in the exercise. Okay, now let's move on the PPT tutorials for the three-phase systems, the transformers, of course, it is systems too. Okay, here we try to talk in detail about the three-phase transformers. Okay, here I try my best to explain each of the concepts meanings and the meanings of each parameters probably appear in the questions of the three-phase systems. Okay, so that even if you have different problems with the three-phase transformers, you can correctly understand and correctly explain each of the concepts. Okay, once again, let me try to emphasize that, for the three-phase transformer, no matter it is a star-star connection, delta connection, or star-delta connection, that the transformer's efficiency definition is the same, It's the same. Okay. So this formula once again, and the first one telling you that the general definitions of the efficiency issues. So the efficiency issues has been defined as, once again, the output, real powers and secondary. So remember, output, real power, and secondary. Input, real power, and primary. So this is the basic definition. So the formulas, following these formulas, the one following this formula is just the one case of it. Okay. So here suppose the output voltage, output powers P out. Then the input powers related to the out powers. So by adding internal loss. So the P loss here is the internal power losses of the transformer. Okay, that's the meaning of it. Okay, so output powers plus internal losses. Of course, you can also say that output powers is the internal minus losses. Okay. This also can be run into the P in minus P plus over the P in, okay, times, okay, same. Okay, the same, right? So here we just write down out, right? Out over the, okay, out plus losses. But sometimes maybe you know the input powers. So input powers minus the losses over the input power that, okay, times the 100%. That's the efficiency too. So and the right college students, you should know the logic here. And here, so this is the secondary, okay, referred output powers, secondary referred output powers, okay. Okay, so although here, so we said secondary voltage, okay, secondary currents, okay, and secondary loading power factors. So this is secondary output powers, the powers to load, or we say the real powers to load. So here you can use, okay, the loading currents, the loading voltage, the loading power factors to estimate the loading powers. Okay, because in the case, right, many cases, this is just the meaning of it. Okay, in practice, maybe depending on what is given, you can estimate that the secondary output powers. Do not stick to these formulas. Okay, once again, okay, sometimes you need to, based on, okay, the situations, to use in different way to estimate the output powers. Okay, not always try to find out the specific symbol used in these symbols, right? In these formulas. Okay, and for the, okay, for the, okay, input powers, so it includes three parts. So look at here. So the secondary output powers, this is secondary output powers, and the core losses and copper losses. Okay, so here I'll write down some words that can remind you. So most of the students may, right, not, okay, pay attention to it. So that the copper losses. So once again, the copper losses, which varies, right, varies with loading currents. Okay, so depending on the internal resistance of the transformer, depending on the loading currents. Okay, and the core losses. Core losses are for the transformer cases, that core losses which proportional, okay, related to the voltage applied. okay, various voltage, right? But the voltage usually is okay, a constant, so that core loss is constant, right? Let me okay. Okay. This is very important because okay, some of you, right, just remember, oh, the core losses is a constant, but you don't know why. Okay, but here telling you why. So the core losses, which varies, is the voltage applied. For the transformer, if the voltage, right, keeps normal change, then the core losses keeps normal change. That's the meanings of it. This is 2 points I would like to write, emphasize here. So the things left, of course, right, how to do the calculations of it. The thermal that here, so you can look at that for the core losses, which depends on the currents, So here, the secondary currents, secondary referred, so this secondary referred internal resistance, secondary currents. Okay, so but you can also use in the primary currents, a primary referred, right, resistance is okay. Okay, the same things. Primary, okay. So some students sometimes maybe you know the primary referred currents and the primary referred equivalent circuit, equivalent resistance. So do not use it, okay, the primary referred current but secondary referred resistance or secondary referred currents or primary referred resistance. So every year we do have very few students are confused of this one, or even anyway, so they just confuse some things like this. So using a wrong approach to the calculations of the core losses. Okay, pay attention to it. So you can use a primary referred internal resistance and primary referred currents. That's okay, but remember it. And here is the secondary referred voltage, secondary referred currents, and power factors, and secondary. Okay, so the secondary, that is the loading power factors. Okay, the secondary loading power factor, primary loading power factor, slightly different, but normal big difference for our practice. So if you also can use in the primary referred voltage, primary referred currents. Okay, that's very similar because when you do the calculation, you use the transformation ratios. So the relationship between the voltage currents always right be very similar to it. And also, I would like to showing you in transformer, primary and current primary equal to secondary and current secondary equal to base. Okay. So okay, take a little more times here because that we need you understood, right? Fully, right? Understand these formulas. So for the VSIS, it is totally equal to VPIP, which is the total power. Okay, the apparent powers. They are the same. They're same. Now you can write use such formulas correctly under whatever conditions. Okay, that will be great. Okay, I believe that you have no more questions on this transformers efficiency definitions. So although we just have one formula here, but the meanings, you should understand each of the symbols meanings here. Okay, not confused of it. Okay, so sometimes you can use a different way to gauge the same quantities. Okay, but understanding the meanings behind it. Okay, so now we go ahead to see examples. Showing you more details about the nameplates meanings of the transformers. Okay, tutorial example 1. So now we straightforward. In an office building, a 3-phase casting transformer with a minus 2.5 tamping is installed to supply electricity to various loads. It is assumed that the supply voltage on the primary side is maintained at 11 kV. And so this means that this transformer and the primary side, the 9 voltage has been maintained at 11 kV. Okay, so primary 9 voltage, 11 kV. But remember that there is a tamping errors. So the actual input voltage lower than this one. Okay, minus 2.5, right? Okay, errors. That's it. Now, the specifications of the transformer. So rating total powers. So a 2000 kVA, this is the total apparent rating powers of the transformer, 3-phase case. Okay, so now the rating, the high volt side rating. So the rating is 11 kV and the high volt side. But here it already said that this transformer has minus 2.5 tampings already have, right? Sometimes it is allowed. This means that this transformer allowed to have plus minus 2.5, right? Tamping errors. Okay, that means the engineer will install this transformer plus minus 2.5 percent of the tamping errors is allowed. It's not. And also plus minus 5% of the errors is allowed because of the temperatures, because of the source. So this just telling you the allowed errors for these transformers. But this term already be giving that the supply side be maintained at 11 kV and the tamping errors minus 2.5. Okay, this is the given conditions of it. And a rated low voltage side. So if the primary exactly 11 kV, then the secondary will be 400 volts if it is full load. Okay, that's the meaning of it. And the working frequency 50 Hz. And here, so impedance at 75 degree. This means that the impedance, the internal impedance of the transformer in a per unit system when it is working at full load, 75 degrees, that is full loading operating temperatures. Okay, so No load losses. No load means that open circuit. So this is the open circuit, right? Losses, which is the core losses. Okay, that's the meaning of it. So which can be obtained by doing the open circuit tests. Now, load losses at 75 degrees. I said 75 degree means the full load case. Okay, the full load, right? Copper losses. Losses and full load causes are currents. So this is the meaning of it. But this is a three-phase transformer for getting the total powers, not for one phase of it. Okay. Impedance also is full load case. Okay. Right. That's it. Because the resistance change with temperature. So here the main thing is the resistance. The impedance, right? The inductance changing with the right frequencies. So remember that. Sorry, reactance changing with the frequencies. But here frequency is given. Okay. So this is specifications. Based on this one, we can got several right parameters, internal parameters of the transformer by doing simple right calculations. And the question is that find out the efficiency of the transformer, which is connected to a load with a total rating of 1,500 kVA. So this loading itself, this means that it is not full loaded. It is connected to a 1,500 kVA, which rating, this is a three-phase loading rating at 380 volts 9, 220 volts phase. So this is the loadings rating. Okay, this is load rating. Do not confuse with the rating of the transformer. Okay, that's rating. So this is the loading information. B, find out the short circuit currents and both primary and secondary if all the secondary terminals are accidentally grounded. So part B is just thinking that is a short circuit case. Now, because this is three-phase one, once again, that try to solve the right three-phase transformer based on the concept of a single-phase transformer. So we should have the per phase equivalent circuit in your mind. So then you can find out per phase internal impedance, per phase right loading impedance, and per phase input voltage, per phase output voltage, per phase input currents, per phase output currents. Here, I will not draw the equivalent circuit, and supposing that the circuit in your mind, which is very simple that we talked in the tutorials in previous two weeks. Now, efficiency in the transformer. Now, we do not know, so what's the connection with the transformer? As a matter of fact, we do not know necessary to know it. We suppose it is a star-star connection. Then we can estimate the per stars phase values. And estimate per star phase value. Okay. Now we're using the per star phase values to do the calculations on the transformers. First, now let's looking at the transformers itself's internal parameters. Refer to lower side. You can refer to upper side. Okay, now here refer to lower side. Okay, I write clearly. Okay, first, assuming it is a star connection, and it is a star connection of loading. Okay, as a matter of fact, it doesn't matter. Here we assume it. Then for the transformer impedance, refer to lower side. So the rating currents, the rating powers, root square that 9 rating voltage. This is 9 voltage. Okay, so this is a 9 current. Okay. So this is the per phase 9 current, a per phase currents, right, in the star-star connection. This is a rating currents. Okay, rated currents. Now, the base impedance refer to secondary. So now the base values. So the secondary, okay, 9 voltage square. So we use the 9 voltage, okay, and the total powers, okay. Okay. Now here we use, okay, remember, okay, so this is 9 values, this is total powers. Okay, 3-phase total phase. Three-phase total powers. Okay. Then, so given that the transformers, okay, internal impedance refer to secondary. This is internal impedance refer to lower side. Okay. And then look at here. So from the, okay, loading loss, that is copper loss. Okay, this copper loss. This is base values. This is copper loss. So using the total copper loss, using the rating current, this is line current or phase current for star connection. So 3-phase, this is 3-phase. Okay, the total copper losses, the per phase, okay, internal resistance refer to low voltage side. Okay, so you can got the per phase internal resistance refer to lower side. And similarly, that you can got per phase, right, internal reactance refer to secondary side. Similarly, so you can go to right, okay, per phase internal reactance referred to the lower side. So based on the given specifications, we got to rating internal, right, rating secondary currents, the secondary base impedance, and the secondary referred internal per phase impedance, secondary right referred per phase reactance resistance. Okay. Similarly, that for the load, that it is given that load power factor is 0.85, and impedance angles can be found out. And the loading that it is given the loading rating at 380 volts 9. So this is 9. Loading line voltage, and the total rating powers, which is 1,500 kVA. So this is the per phase load powers. Phase load impedance. For star phase load impedance. Okay. Load resistance. And star phase load reactance. Okay, we have the transformers per star phase internal resistance, per star phase internal reactance, and now we find out the per star phase load impedance, and per star phase load resistance, per star phase load reactance. So in the loading cases, we can ignore the excitation branch, right, impedance. Okay, so that the total circuit, currents can be estimated easily, by adding the loading impedance together with the transformer impedance. Okay. Generally, so when the system is loaded, so we can ignore the excitation branch reloaded. Okay. So now we just based on the transformers to find out the total input voltage. The total input 11 kV, that equivalent to 411 kV. Okay. This is the 9 voltage. Okay, for 11 kV equivalent to okay. So now the primary maintain at 11 kV. Okay. Transformation ratio can that the secondary maintain at 400 volts. Now the primary where it is right for loaded, the primary now has a minus 2.5% of the tapping errors. So the refer to the secondary, it has minus 2.5% down the voltage. So this is down voltage. Over root 3 is the phase voltage. the per phase input voltage referred to lower side. Okay, per phase input voltage referred to lower side. Okay, that is 225, right? 17 volts, which is higher than the rating voltage required for loading, which is 220. Now, so this is the per phase input current referred to secondary. Yeah, referred to secondary. So, so that is the currents over, okay, is the voltage over the total impedance. We're gonna have total impedance. Yeah. So this is currently referred to the lower side. So the voltage referred to lower side, and the total impedance. Okay, looking at total impedance. So in the previous station, we got the resistance of transformer, resistance of the loading, reactance transformer, reactance of loading. That you can bring in. You can do in the calculation in constant number forms or polar forms. You can find out the currents to loading currents. This is loading currents, actual currents. So this current is slightly smaller than rating currents. Okay, so this is loading currents. And also you found that the output right currents that lagging the output voltage by angles. This angles a little bit right larger than angles of loading itself, because the internal impedance of the transformer contributed to this impedance angles. Okay, that's the meaning of it. Efficiency. Okay, so now we can estimate the output powers. So the output powers we can use in the loading powers to the calculation. So now the per phase, we using the per phase, right? We are doing the per phase power calculation. Okay. So you can use the total. That's the same, right? So a per phase output powers or per phase loading powers in this case. So the loading impedance resistance. This is loading resistance. Okay, resistance loading current square. You can use a different way to the calculation. Okay. Because there probably some students later on may ask some questions here. So here I'm using such a way to estimate the loading powers. You may use different formulas to estimate loading powers, loading power consumptions, but which is different from the rating power. Okay, do not confuse of it. Okay, because some students may they're using the rating powers as the output powers. Okay, this is different from the rating powers. Okay, so from the rating powers we just estimate the equivalent impedance of loading. Okay, losses. So the losses including that R losses or core losses and the copper losses. Now here, so the core losses be given, but for 3 phase here we got per phase values. Okay, and for the internal copper losses, so here the secondary referred currents IP phase we estimated 2.26 kiloamperes and square and times the internal transformers resistance. Transformer resistance. Sorry. Internal transformer referred to secondary. Secondary referred currents. Secondary referred internal resistance of transformer, both primary and secondary together. So you can get the losses. So therefore, the efficiency can be easily found out. Okay. Now, for short circuit case, that the per phase, right, short circuit secondary currents, So the transformer impedance, the loading impedance be 0. This is easy to understand. So the loading short circuit, when it is short circuit, the per phase input voltage and the per phase total impedance, which is the transformer itself. So you can estimate that this short circuit currents much larger than the loading currents. Much larger than this one. Almost 20 times, 20 times, because the internal impedance is about 6% of the base values. Here about 1/20th, right? Now, so this is the short circuit currents referred to secondary. Then you can transfer, refer to primary by using the transformation ratios. Transformation ratio, the definition. You can find out, refer to primary. So this is the tutorial example 1. Then we have a relative, detailed explanation on it. We also have the tutorial example 2. That very similar to the first one, but here we suppose that we know the efficiency of the transformer, given that the transformer's internal impedance, internal resistance, and the internal reactance. Look at here. So this transformer rating at 100 kVA, 3-phase starter transformation, and has a transformation ratio 11 kV over 380 volts, and has a full load efficiency of 96%, and per unit impedance and per unit resistance of 0.05, 0.03 respectively. So this is the per unit values given. So now, so if you are going to do the short circuit test and open circuit test, then how to do it, and what is the possible readings of the of the open circuit test reading and short circuit test readings. So this is a reversed question. Suppose the efficiency we already got it, and now so you are required to estimate the possible short circuit test and open circuit test readings in terms of the input voltage, currents, powers. So it's the reverse of the question 1. Let me see. Oh, there are maybe at the toppers, this is 2.2 or 2.3, right? Forgot. Maybe. Okay, so these questions, I think, so let the questions be read by yourselves because the answer already be there. So If you now, right, do you still have some questions on the three-phase transformers? So you can ask me at this moment, or write to me after lectures. Okay. So please read tutorial example 2, and also the examples 9 to 11 in the exercise books. Okay. Try to find out questions you have and ask me before the final examinations. Okay, I think this is the end of today's tutorial. Okay, I have no more time to deliver all of the examples. So thank you. So you can still take the time to ask me questions. Do not write just me talking about example, but I would like to hear from you whether you have questions, whether you have understood what I taught. Right?